Engineering properties of rocks is a rather generalized term and might be understood all such properties of rocks that are relevant to engineering applications of these materials either after their extraction from natural beds or without extraction, that is in situ conditions. The first set includes all those properties for which a rock must be tested for being selected as a material of construction, for example, as a building stones, road stones or aggregates for concrete making. The second set of the properties would include the qualities of a natural bed of rock mass as and where it exists that would determine in the suitability or otherwise as a site for proposed engineering project. Obviously, in both cases the economy and safety of an engineering project are greatly dependent upon the proper understanding and the determination of the properties of rocks. A combination of laboratory testing and small samples, empirical analysis and field observations should be employed to determine the requisite engineering properties. Rock properties can be divided into two categories. One is intact rock properties and rock mass properties. Intact rock properties are determined from laboratory tests on small samples typically obtained from coring, outcrops or exposures along the existing cuts. Common engineering properties typically obtained from laboratory tests includes specific gravity, point load strength, compressive strength, tensile strength, shear strength, modulus and durability. Rock mass properties are determined by visual examination and description of discontinuities within the rock mass following the suggested methodology of the International Society of Rock Mechanics, that is ISRM 1978, and how these discontinuities will affect the behavior of the rock mass when subjected to the proposed construction. The following physical properties are considered to be important for a rock stone as a building material. One is important physical property is crushing strength. Crushing strength, it is also termed as compressive strength of a stone and may be defined as a maximum force expressed per unit area which a stone can withstand. Any force behind the compression strength will cause a failure of the stone. Mathematically, compressive strength is expressed by simpler method as follows: CO is equal to P divided by A, where CO is the compressive strength, P is the loaded failure, A is the area of cross section of stone under P. The determination of compressive strength of a building stone involves making standard test specimens which are either cubes of 5 cm side or it may be a cylinders of length diameter ratio of 2 or 2.5. These specimens are then loaded gradually one at a time after placing on the base plate of a universal testing machine till the first crack appears in the specimen. Any further loading will crush the specimens. The compressive strength determined in this way using the above relationship is called unconfined or uniaxial compressive strength because this test specimen has no lateral support. When the compressive strength is tested by a method providing a lateral support as by keeping the specimen in a special cell filled with a liquid and a pressure, the value obtained is called a confined or triaxial compressive strength. The crushing strength of a rock depends on number of factors such as its mode of formation, its composition, its texture and structures, its moisture content. Igneous rocks being crystalline in character, compact and interlocking in texture and uniform in structure possess very high crushing strengths compared to a sedimentary and metamorphic rocks. In the sedimentary and metamorphic rocks, presence of planes of weakness such as bedding planes, foliation, schistosity and cleavages greatly affects the compressive strength both in direction and magnitude. The sandstones may show a very low crushing strength when loaded parallel to the bedding planes than when loaded perpendicular to the same structure. Except for sandstones, quartzite and some gneisses, most other sedimentary and metamorphic rocks are composed of clayey, calcareous and hydrated silicate minerals which are inherently weak in strength. Crushing strength of a common types of building stones is generally higher than the loads that they are supposed to withstand in ordinary type of building constructions. The compressive strength of some rocks are as follows. It is expressed in kilograms per centimeter squares. So, dolerite, the range is 1500 to 3500, basalt is 1500 to 3500, quartzite is 1500 to 3000, granite is 1000 to 2500, marbles is 700 to 2000, gneisses is 500 to 2500, sandstone 200 to 2000, limestone 200 to 1500. Now, let us coming to the another important physical property is transverse strength. It is defined as the capacity of the stones to withstand bending loads. Such loads only rarely involved in situations used, but when a stone is intended for use as a beam or a lintel, its transverse strength is determined as modulus of rupture using the following relationship: R is equal to 3 W L divided by 2 B D square, where R is the modulus of rupture, W is the weight at which the sample breaks, L is the length of the specimen, B is the width of the specimen, D is the thickness of the specimen. It has been found that the stone's transverse strength is generally 1/20th to 1/10th of their compressive strength. Shear strength. Shear strength of a stone is also not commonly determined except when the stone is to be used as columns. Shear strength is the resistance offered by a stone to shear stresses which tends to move one part of a specimen with respect to the other. It is obtained by using this relation S is equal to P divided by 2A, where P load at failure, A is the area of cross section of the specimen. It has been observed that shear strength of most common building stones lies between 70 to 140 kilograms per centimeter square. Tensile strength. It may be determined directly or indirectly. The tensile, that is nothing but the pulling strength that has to be applied to a material to break it, it is measured as a force per unit area. The direct method would require elaborate means to avoid bending while applying a tensile forces by gripping the specimens at the ends. It is very complicated process, and since the tensile stresses are seldom required accurately, an indirect method is commonly applied. The indirect method is called the Brazilian test, consists of loading a test cylinder diametrically in such a way that the applied loads would develop a tensile rupturing along the diametrical plane of the specimen. Loads are gradually increased till the cylinder fractures. The load P at rupture, the tensile strength Ts is calculated by using the formula Ts is equal to 2P divided by mu dl, where d is the diameter of the specimen, L is the length of the specimen. Porosity. Porosity is an important engineering property in the sense that it accounts for the fluid absorption value of the stones in most cases, and also that a higher porosity signifies a lesser density, which generally means a lesser compressive strength. The shape, size and nature of the packing of the grains of a rock give rise to the property of porosity or development of pore spaces within a rock. Numerically, it is expressed as the ratio between the total volume of pore spaces and the total volume of the rock sample. Porosity is commonly given in percentage terms. Then presence of interlocking crystals, angular grains of various sizes are abundant, and abundant cement materials are responsible for low porosity of stones. Porosity value for a few common building stones: the granite is 0.1 to 0.5%, basalt is 0.1 to 1%, sandstone 5 to 25%, limestone 5 to 20%, marble 0.5 to 2%, quartzite 0.1 to 0.5%. Absorption value. Absorption value defines the capacity of a stone to absorb moisture when immersed in water for 72 hours or till saturation. It is generally expressed in percentage terms of original dry weight of the stone sample. It may be obtained from the relationship absorption value is equal to WS minus WO divided by WO. That is nothing but the WS is the weight at saturation, WO is the dry weight. And coming to another important property of rock or physical property of rock is permeability. It is the capacity of a rock to transmit water. It is very important in solving some engineering problems such as those of connected with dams, reservoirs, water supply and sanitary works. Sandstones and limestones may show in some cases is high values for absorption or even 10% or even more. Selection of such highly porous varieties of these stones for use in building constructions, especially in most situations, would be greatly objectionable. Presence of water within the pores not only decreases the strength of the rock, but also makes the stones very vulnerable to frost action in cold, humid climates. Density. It is defined as weight per unit volume of a substance, but in the case of rock, it is not only the solid mineral matter which only accounts for the total volume of a given specimen. A part of the rock may comprise of porous or even open spaces which may be empty or partly filled or wholly filled with water. According to three types of densities may be distinguished in rocks, and one must be clear about the type of density referred to, either dry density, bulk density and saturated density. Abrasive resistance. It is more qualitative than quantitative property and may be broadly defined as the resistance which a stone offers to rubbing action of one kind or another. Frost and fire resistance. Many building stones show a quick disintegration when used in situations involving frost formation, that is nothing but excessive cold or heating. Frost causes disintegration by expansion of water on freezing within the rock pores. In the case of fire, it is unequal expansion in the different mineral components and also at a different depths from surface inwards. This effect becomes more pronounced when the rock is first heated and then suddenly cooled by water. Heavy stones including granites crumble to pieces under such a treatment. Only compact and massive sandstones and quartzites will have reasonably well in fires and heating places. Mineralogical compositions. As rocks are ultimately made up of smaller units of the mineral, their properties depend upon the nature and composition of these minerals. It has been observed that rocks composing chiefly of silica, that is nothing but SiO2, especially in free form, are the strongest in all respects. Quartzites, sandstones and granites are some of the examples given for this type of mineral compositions. The carbonate rocks show a wide variation in their properties, and particular deposits of these rocks has to be tested by taking a random representative samples before the stone is recommended for use in engineering constructions. Presence of some mineral even in small quantities is to be viewed with caution while utilization of building stones. The minerals are mica, gypsum, sulfides, tremolite, flint, chert and clays. These destroy the inherent strength of the rock. Textures and structures. Textures defines the size, shape and mutual relationship of the mineral components in a rock, whereas structure determines the development of large scale features in the rock mass as a whole. Rocks may be coarse grained, medium grained or fine grained. The fine grained equigranular textured rocks are better building stones compared to a coarse grained and inequigranular rocks. Structurally speaking, such features as bedding planes, foliations, cleavages, joints and flow structures which might not be fully represented in small sized test specimens, but which may be present in rocks masses on a large scale have to be given considerations. Resistance to weathering, that is durability. It is essentially a geological character of a stone that is commonly determined by its composition, texture and structure on one hand and the climatic environment whereas the stone is ultimately used on the other hand. Nothing is everlasting, stones being included, but the rate at which a rock deteriorates or decay under the attack of natural processes is highly variable. A stone may remain almost fresh and untarnished for 500 years or even more when used in the interior of a building, but the same stone used on the exterior might get pitted and weathered badly within 100 years. For example, granite. Similarly, the limestone used in building constructions in industrial townships may wither badly and quickly due to the reaction with sulfurous acid polluted air, whereas the same rock has changed, but only a little in temples, ports and historical buildings and many centuries old. An engineer and especially a town planner has to bear in mind the fact that rocks are also live and sensitive to the environment in which they are placed. Durability of a stone can be experimentally determined by subjecting the stone samples to disintegrate action of sodium sulphate. Test specimens generally of 5 cm side cubes are dried perfectly and weighed. They are suspended in 14% solution of sodium sulphate for 4 hours at 27 degrees Celsius and then air dried and oven dried at 105 degrees Celsius. The stone samples are subjected to 30 such cycles and loss of weight determined, which gives a measure of the durability of the rock. Greater the loss in weight after these cycles, poorer is the durability of the stone. General characters. Cost. It is an important consideration as general character. A stone may be quite suitable for use in building constructions on first 2 considerations, but still it may not find use for the simple reason that it is uneconomical. Cost of a building stone depends upon its availability, accessibility and workability. Good quality building stones are not available everywhere. Their transport from one place to another might be a very costly affair. Color. Color is the property of appeal and gets involved only where the stone is used in constructions exposed to public view. For stones to be used in foundations in dams or in situations where they are ultimately to be given covering, color of a rock has no relevance in its selection. In the case of residential or official buildings, however, it becomes a property of major importance. The color of a rock is a geological character depending upon the type of rock or more precisely upon the composition of rock. Granites are light colored, basalts are dark and sandstones are lighter shades. The elasticity of a rock indicates their deformation under loads. The deformation is recovered when loads are removed. It is determined in accordance with the Hooke's law, which states stress is directly proportional to strain. It is expressed by the relationship where epsilon is the modulus of elasticity and E is the strain and where Q is the stress. It is also termed as Young's modulus. Rocks are highly anisotropic so far as their elastic constraints are concerned. They show all varieties ranging from perfectly elastic to perfectly inelastic. This depends on their composition, texture and structures. It is possible to group the rocks into 3 categories based on their modulus of elasticity. One is quasi-elastic, semi-elastic and non-elastic. Quasi-elastic, these are rocks in which the stress and strain relationship is expressed by almost a straight line till the point of failure. Such rocks includes a massive, densely packed, uniformly structured varieties of igneous, sedimentary and metamorphic groups such as cyanides, diorites, dolerites, gabbros, basalts and quartzites. Semi-elastic rocks. Semi-elastic rocks are coarse grained, slightly open packed with some porosity and very minor in any structure, discontinuities. The coarse grained igneous rocks like granites, some massive compact sediments like sandstones and dolomites may often show a semi-elastic properties. In this group, the curve indicating the modulus of elasticity, such a characteristic that its slope tends to decrease with increasing loads. Non-elastic rocks. Non-elastic rocks are those in which the stress-strain relationship tends to break in two zones, a initial zone of steep slope followed by curve of least slope. Any type of rock that satisfies the above considerations may be used as building stones. Granites, sandstones, limestones, marbles and quartzites and others like dolerites, cyanides, basalts and gneisses etc. or some of them are not available because they do not possess all the requisite properties. Let us see one by one. Granites. These are the most commonly used building stones of all the igneous rocks. They generally possess all the essential qualities of a good building stones, showing a very high crushing strength, low absorption values, least porosity, interlocking texture, variety of appealing colors and susceptibility to perfect polish. India has got good reserves of granitic rocks. The Archean group of rocks of peninsular India are comprised chiefly of gneisses and granites. Sandstones. Massive sandstones consisting of closely interlocking and angular grains and free from structural defects find extensive use of building stones. Ferruginous and calcareous varieties should not be used for exterior work, especially in industrial towns. Argillaceous sandstones are generally weak in character. Massive varieties with a siliceous cement possess a sufficient strength and are easily workable. India has got immense reserves of sandstones fit for construction purpose. Vindhyan sandstones are fine grained in texture and available in abundance in a variety of colors like white, cream and deep red and even grey color. The Gondwana formations of India have also yielded a very good quality of sandstones. Limestone. Limestones, these sedimentary rocks are also very extensively used as buildings stones, but all types are not suitable for this purpose. They vary greatly in their physical properties, thus in crushing strength they may be as weak as showing values much below 300 kilograms per centimeter squares or as strong as 1500 kilograms per centimeter square or even more. A similar variation in other properties like absorption, specific gravity and porosity may be observed. The use of these limestones as facing stones, even if they are sufficiently hard, should be avoided in situations where the air is polluted with industrial gases. Second is the air from sea can approach them easily. Marbles. These are metamorphic rocks that are used for ordinary structural work as well as for decorative purposes. Marbles are vary in texture, color and composition. Their absorption value is generally below 1% and normally they possess a sufficient crushing strength. They have been extensively used as decoration stones and this is because of their susceptibility to brilliant polish and beautiful colors. Most important source of commercial marbles in the crystalline formations of Rajasthan, one is Makrana in Jodhpur, where we find a white and pink marbles. The second locality is Karwa in Ajmer, where we have green and yellow marbles. The third location is Kishangarh and Jaipur are the famous for black and dense marbles. Slate. It is another metamorphic rock characterized by a perfect cleavage and because of this property it does not find any use in building stones except for paving and roofing purposes. In India, slate deposits occur at quite a few places, of which Kangra, that is in Himachal Pradesh, Pirpanjal, that is in Jammu and Kashmir, and Rewari, that is in Rajasthan. Conclusions. It is a well known fact that rocks play a vital role in constructing the structures which are destined to be strong, appealing and economical. All the factors which have been considered so far give a clear guideline for an engineer to choose the right type of naturally occurring rocks or stones to build such structures. By choosing all the properties judicially in conjunction with one another, it is possible to adhere to the safety regulations prescribed in building standards. A combination of laboratory testing of small samples, empirical analysis and field observations should be employed to determine the requisite engineering properties.